The universe holds more secrets than we can possibly imagine. Our cosmic home is filled with phenomena so strange they defy our current understanding of physics. This journey explores 30 of the most baffling cosmic mysteries that continue to stump the world's brightest astrophysicists. You will uncover the true nature of reality, from the invisible forces shaping galaxies to signals that might be messages from another world. We will wrestle with why the cosmos is expanding faster than it should, and what lurks in the vast, dark voids between galaxies. Which of these cosmic riddles do you find the most unsettling? Our universe is held together by a ghost. We see its fingerprints everywhere, a cosmic scaffolding that dictates the very motion of galaxies, yet the substance itself remains utterly invisible. This is the profound mystery of dark matter. It makes up roughly 27% of everything that exists, a dominant, unseen component of reality. We know it is there because of gravity. Stars on the outer edges of spiral galaxies whirl around at speeds that should tear them free, flung into the intergalactic void. But something holds them in place, an immense halo of invisible mass whose gravitational grip is the only thing keeping those stars from flying away. This same unseen force binds entire clusters of galaxies together, warping the fabric of space-time so severely that it bends the light from distant objects behind it, an effect called gravitational lensing. So what could this invisible cosmic glue possibly be? The leading candidates are as strange as the phenomenon itself. Scientists theorize it could be WIMPs, weakly interacting massive particles, hypothetical entities that are billions of times heavier than a proton but barely interact with normal matter. Or it could be actions, incredibly light particles that could flow through the universe like an intangible wind. Countless experiments deep underground, in abandoned mines and beneath mountains, are searching for the faintest whisper of a collision, a sign that one of these ghostly particles has finally been caught. Discovering the true nature of dark matter is not just about identifying one missing ingredient. It is about rewriting our fundamental understanding of what the universe is made of, revealing the hidden architecture upon which every galaxy is built. But if dark matter is the ghostly glue holding the cosmos together, its partner is a phantom force tearing it apart. Dark energy is the name we have given to this inexplicable pressure, a repulsive force that is causing the expansion of the universe to accelerate. Its discovery in the late 1990s was a profound shock, turning our cosmic forecast on its head. By observing distant supernovae, astronomers realized these stellar explosions were fainter and farther away than they should have been. The only possible explanation was that the fabric of space itself was stretching at an ever-increasing rate, pushing galaxies apart with a force that grows stronger over time. While dark matter pulls with the force of gravity, dark energy pushes with a strange anti-gravity effect. It now makes up a staggering 68% of the universe, the dominant component of reality, and we have no idea what it actually is. The leading and most unsettling theory is that it is an intrinsic property of empty space itself. According to quantum physics, a vacuum is not truly empty, but a bubbling sea of virtual particles that constantly flicker in and out of existence. This vacuum energy could be generating the repulsive force we observe. The problem is when physicists calculate how strong this energy should be, the theoretical answer is wrong by a factor of 1 followed by 120 zeros, a number so colossal it is the greatest mismatch between theory and observation in the entire history of science. This fundamental problem points to a deep flaw in our understanding of physics. The ultimate fate of the cosmos hinges on the true nature of this dark energy. If it continues as it is, the universe faces a big freeze where galaxies fly so far apart that the sky goes black, stars burn out, and everything approaches absolute zero. But if the force strengthens, it could lead to a far more violent end, the Big Rip, where the fabric of spacetime itself is torn asunder, shredding galaxies, solar systems, and even atoms in a final catastrophic moment. We are left staring into the void, confronted by a force that constitutes the majority of existence, yet remains a complete and utter mystery. This phantom force accelerating the universe is not the only invisible hand guiding our cosmic path. Our entire galaxy, along with countless others, is being pulled on a mysterious journey towards a specific point in the darkness, a region known as the Great Attractor. Think of it as a colossal river in space, a flow of galaxies all moving in the same direction, with our Milky Way caught in its current. This gravitational anomaly exerts a pull so immense it overrides the general expansion of the universe in our local neighborhood, drawing us and thousands of other galaxies toward an unseen focal point. The destination lies about 250 million light-years away, in the direction of the constellations Centaurus and Norma. Yet, for a long time, this region was a complete blind spot for astronomers. It sits directly behind the plane of our own Milky Way, an area we call the zone of avoidance. Here, thick clouds of cosmic gas and dust obscure our view, blocking almost all visible light from what lies beyond, like trying to see a distant city through a dense, perpetual fog. This made the Great Attractor one of the most frustrating puzzles in modern astronomy, a titanic force whose source remained hidden behind the veil of our own galaxy. So what could possibly possess such gravitational power? Early theories suggested it was a massive concentration of dark matter, a node in the cosmic web with enough invisible mass to tug on an entire supercluster of galaxies. As technology advanced, allowing us to peer through the dust with X-ray and radio telescopes, a clearer picture began to emerge. We now believe the Great Attractor is not a single, unimaginably dense object, but the gravitational heart of an enormous supercluster, the largest structure we are a part of, known as Laniakea, a Hawaiian word meaning immense heaven. Visualize Laniakea not as a sphere, but as a vast cosmic watershed. Every galaxy within its bounds, including our own, is flowing down gravitational slopes toward the same central valley, the Great Attractor. This region is likely a supercluster in its own right, a dense knot where many galactic filaments meet, creating a gravitational focal point of staggering proportions. Yet, even this may not be the end of the story. The pull we feel might be caused by something even larger and more distant lurking behind the Great Attractor itself, a shadowy entity known as the Shapley Attractor pulling the puller. The mystery has evolved from searching for a single monster in the dark to mapping the subtle currents of the cosmic ocean, revealing a universe where even the largest structures are mere waypoints in a much grander and still hidden gravitational flow. This relentless gravitational current is not the only mysterious signal pulling our attention across the cosmos. Out in the deepest darkness, the universe flashes. For a mere thousandth of a second, a burst of radio waves erupts with more energy than our sun emits in 80 years. Then, just as suddenly, it is gone. These are fast radio bursts, or FRBs, and they are one of the most transient and powerful phenomena we have ever detected. The first one was discovered in 2007, hidden in archived data from a radio telescope in Australia, a single, brilliant spike that seemed to come from nowhere. For years, these events were written off as potential glitches until we found more, confirming they were real and of cosmic origin. Most of these bursts are loners, a single, catastrophic flash from a galaxy billions of light-years away that never repeats. But one, known as FRB 1211-2, shattered that pattern. It repeats, sending out brilliant, unpredictable pulses from a dwarf galaxy 3 billion light-years distant. This repetition was the key that unlocked a deeper mystery, allowing astronomers to finally pinpoint a host galaxy for the first time. So what cosmic engine can possibly produce such a staggering amount of energy in such an impossibly short time? The leading suspects are some of the universe's most extreme objects. A magnetar, a type of neutron star with a magnetic field so intense it could strip the information from a credit card from halfway across the moon, is a prime candidate. A starquake on such an object, a sudden cracking of its rigid crust, could release a flash of energy that we see as a fast radio burst. Others propose violent collisions like two neutron stars merging into one, creating a final, brilliant shout of radio waves. Yet, the sheer power and bizarre nature of some bursts have prompted more exotic, though far less likely, explanations. Could we be seeing the signatures of advanced technology, like massive interstellar light sails powered by focused radio beams, a leakage from an unimaginably powerful alien transmitter? While this is the most speculative idea, it highlights just how perplexing these signals truly are. Vast arrays of radio dishes now scan the skies, waiting for the next flash, hoping its unique fingerprint will finally reveal the identity of the cosmic flashbulbs that illuminate the dark. While fast radio bursts flash and vanish in an instant, another cosmic mystery unfolds over years, a slow, irregular dimming that defies all conventional explanation. A star, known officially as KIC 8462852 but popularly called Tabby star, behaves like no other. Located about 1,400 light-years away, it was discovered not by a team of professional astronomers but by citizen scientists, volunteers sifting through public data from the Kepler Space Telescope as part of the Planet Hunters project. They were looking for the telltale periodic dimming caused by an orbiting planet. What they found was far stranger. The star's light would drop by staggering amounts, up to 22%, in irregular, asymmetrical dips that lasted for days. It was not the clean, repeating signature of a planet, but something chaotic and massive, as if a swarm of objects of all shapes and sizes were passing in front of the star. The scientific community was captivated, and a frenzy of hypotheses emerged to explain this bizarre light curve. The first, more natural explanation was a colossal swarm of comets, thousands of them, trailing immense clouds of dust and debris that would intermittently block the star's light. Others proposed the remnants of a shattered planet, a field of planetary rubble from a recent catastrophic collision, creating a vast, uneven ring of dust. But the most tantalizing and most speculative idea was that we might be witnessing the construction of a Dyson sphere, a hypothetical megastructure built by an advanced civilization to capture the entire energy output of its star. The irregular dimming could be the shadows of vast, incomplete sections of this cosmic energy farm, a project of unimaginable scale. Follow-up observations have only deepened the puzzle. The star has been found to be gradually dimming over the long term, losing its brightness by a significant margin over the past century. While intense monitoring has shown that the deep, dramatic dips are likely caused by fine, microscopic dust, the source of that dust remains completely unknown. It behaves unlike any dust seen around other stars, and no model of comets or asteroid collisions fully explains the sheer scale and irregularity of the dimming. So the question remains, what is generating this immense, evolving cloud of dust? Is it a natural, albeit extreme, stellar phenomenon we have never witnessed before, or could it be something else entirely? The star continues to be watched, a flickering enigma in the constellation Cygnus, holding its secret close. A star's slow, irregular dimming is one thing, but the cosmos once seemed to shout a single, unmistakable word directly at us. On August 15, 1977, a radio telescope known as the Big Ear was performing its routine, automated scan of the sky, listening to the silent radio hiss of the universe. A few days later, volunteer Jerry Amon was sifting through the reams of printed data, columns of letters and numbers representing signal strength. His eye caught something astonishing, a sequence so powerful and unusual that he circled it in red pen and wrote one word in the margin: "Wow." That single annotation gave the signal its legendary name. For 72 seconds, the Big Ear had recorded a blast of radio waves that was both intense and perfectly narrowband. This is the crucial detail. Natural cosmic objects emit radio noise across a wide range of frequencies, a chaotic smear of sound. The wow signal was a pure tone, a sharp spike on one specific frequency, the kind of signal we would expect from an engineered transmitter, not a star or a quasar. It came from the direction of the constellation Sagittarius, and then it was gone. It never repeated. The signal was so strong that it maxed out the telescope's equipment, reaching an intensity level of 6, represented by the alphanumeric code 6EQUJ5, the very sequence that Jerry Amon famously circled. The search for a repeat began almost immediately, and it has continued for decades. Astronomers have pointed far more sensitive radio telescopes toward that same patch of sky, listening for another whisper, another shout, anything. The silence has been absolute, so what was it? The signal was so brief it rules out a rotating source like a pulsar. It does not match the profile of any known comet or asteroid. It passed the telescope's verification tests, making an instrumental error or a passing aircraft highly unlikely. This leaves two haunting possibilities. The first is that it was a human-made signal reflected off a piece of space debris, though no known satellite or rocket body was in the right position at that exact moment. The second and far more profound possibility is that the Big Ear telescope briefly intercepted a transmission from an extraterrestrial intelligence. A beacon, perhaps, that flickered on for just over a minute, its beam sweeping across our solar system before continuing on its endless journey through the void. The original printout with its circled wow remains a sacred relic in the search for cosmic company, a tantalizing piece of evidence that we might not be alone, a single, perfect note in an otherwise silent symphony. That single, perfect note of the wow signal makes the subsequent silence even more deafening. We have listened for decades, scanning countless stars, and the cosmos has answered only with static. This profound contradiction lies at the heart of one of our greatest existential puzzles, the Fermi Paradox. The universe is unimaginably vast and ancient, with hundreds of billions of stars in our galaxy alone, many of them hosting Earth-like planets. The numbers suggest the galaxy should be teeming with life, a bustling cosmic metropolis. So, the physicist Enrico Fermi famously asked during a casual lunch conversation, "Where is everybody?" If intelligent civilizations are common, we should see some sign of them, from their radio transmissions to their vast engineering projects. Yet we see nothing but an eerie, empty quiet. This great silence forces us to confront several unsettling possibilities. The first is the concept of the Great Filter. This theory suggests that there exists an evolutionary or technological barrier so difficult to overcome that it prevents almost all life from progressing to a spacefaring stage. The filter could lie in our past. Perhaps the spontaneous origin of life itself is an astronomically rare fluke, a spark of chemistry so unlikely that we are the only ones to have achieved it in our entire galactic neighborhood. Or the filter could be ahead of us. It might be that any civilization advanced enough to develop technology like ours inevitably discovers the means of its own destruction, whether through nuclear war, runaway artificial intelligence, or a manufactured plague. In this terrifying scenario, the silence we hear is a galactic graveyard, filled with species that reached our level of development and then vanished. Other solutions are less grim but equally strange. The zoo hypothesis proposes that advanced civilizations are out there, and they are fully aware of us, but they have chosen to place our solar system in a kind of cosmic quarantine. They observe us from a distance, following a strict policy of non-interference, allowing humanity to develop naturally, for better or worse. We would be like an isolated tribe in the Amazon, unaware of the global civilization that surrounds us. Another idea is that the universe is simply too big. The vast gulfs of space and time may be the ultimate barrier. A civilization could have flourished and died out millions of years ago in a distant galaxy. their brief radio signals having passed through our region of space long before we even evolved to build a radio telescope. We are like ships passing in an endless, dark ocean, separated by centuries and light years. The final and perhaps most humbling possibility is that we are, in fact, entirely alone. The complex chain of events that led to intelligent life on Earth, from a stable star to a large moon that stabilizes our climate, to the exact right planetary composition, might be so exceptionally rare that we are a singular accident in a sterile cosmos. In this view, we are not a failed cosmic metropolis, but the first and only inhabitants of a silent, empty house. The Fermi Paradox holds up a mirror to humanity, forcing us to ask not just where everyone else is, but what our own future holds. Are we on the cusp of joining a galactic community, or are we simply the universe's way of trying to understand itself, a fleeting moment of consciousness in an eternal, unthinking night? The profound silence of the cosmos is broken only by our own faint whispers, the robotic probes we have sent into the void. Yet even these human-made objects have behaved in ways that defied expectation, creating a mystery that lingered for decades. This was the Pioneer anomaly. The Pioneer 10 and Pioneer 11 spacecraft, launched in the early 1970s to explore the outer planets, became long-range messengers drifting toward the stars. But as they journeyed beyond Jupiter and Saturn, navigators tracking their radio signals noticed something deeply puzzling. Both spacecraft were experiencing a tiny, unexplained deceleration, a constant, minuscule pullback toward the sun. It was as if a ghostly hand had reached out and was gently applying the brakes. This effect was incredibly small, less than a billionth of the gravity we feel on Earth, but it was persistent and identical for both probes. For years, this tiny signal haunted physicists. Was it evidence of a flaw in our understanding of gravity itself? Did Einstein's theory of general relativity need a modification at the vast scales of the solar system? Perhaps it was a sign of unseen, diffuse dark matter gravitationally tugging on the probes. The mystery persisted until a team of researchers undertook a monumental forensic investigation, recovering decades-old engineering data and building intricate computer models of the spacecraft themselves. The solution turned out to be remarkably mundane yet brilliant. The Pioneer probes were powered by the heat from radioactive plutonium, and that heat had to go somewhere. The team realized that this thermal energy was radiating away from the spacecraft not perfectly evenly. A tiny fraction more heat was being emitted from the back of the spacecraft's main dish antenna, the side facing the sun, than from the front. This created a subtle but constant recoil force, a photon pressure that pushed the craft backward, mimicking a deceleration toward the sun. It was the spacecraft's own warmth, slowly bleeding into space, that had been the invisible hand all along. Yet, even after accounting for this thermal effect, a whisper of the anomaly remains. A tiny, residual deceleration, so small it sits at the very edge of detectability, might still be unaccounted for. This minuscule signal could be nothing more than the final margin of error in our complex calculations, or it could be the faintest hint of something new, a signpost pointing toward physics we have not yet discovered. The Pioneer anomaly serves as a humbling lesson, a reminder that even the most tantalizing cosmic mysteries can have surprisingly ordinary origins, while still leaving the door open just a crack for the truly extraordinary. That subtle, unaccounted-for deceleration from the Pioneer probes is a whisper compared to the cosmic cannonade that constantly bombards our planet. From the depths of space, atomic shrapnel travels at nearly the speed of light, slamming into our atmosphere with energies that dwarf anything we can create in our most powerful particle colliders. These are cosmic rays, and the origin of the most powerful among them is a mystery that has persisted for over a century. Most cosmic rays are relatively low-energy protons, the nuclei of hydrogen atoms that originate from our own sun or from stellar explosions within the Milky Way. But a tiny fraction are different, ultra-high energy cosmic rays that carry the kinetic energy of a professionally thrown baseball, all compressed into a single subatomic particle. When one of these rare, unimaginably energetic particles strikes the upper atmosphere, it does not arrive alone. It initiates a spectacular cascade, a sprawling shower of billions of secondary particles that rain down over an area the size of a small city. This is how we detect them, not by catching the primary particle itself, but by mapping the fallout. Vast observatories like the Pierre Auger Observatory in Argentina cover 3,000 square kilometers of desert with 1,600 water tanks. These tanks are designed to detect the faint blue glow of Cherenkov radiation, a sonic boom of light produced when these secondary particles travel through the water faster than light itself can move in that medium. An array of telescopes simultaneously watches the sky for the faint ultraviolet fluorescence the air shower produces. By combining these signals, scientists can reconstruct the energy and the rough direction of the original cosmic cannonball. And that is where the true puzzle begins. Tracing these particles back to their source is like trying to follow the path of a bullet fired through a hurricane. Space is not empty, it is threaded with magnetic fields. These fields, weak as they are, act like a hall of mirrors for a charged particle like a proton, bending and twisting its trajectory millions of times over its multi-million light-year journey. By the time it reaches us, its path is so scrambled that pointing back to its origin is like trying to find which specific tree a leaf fell from after it has been blown for miles by a turbulent wind. So what cosmic engines are powerful enough to accelerate a single proton to such ludicrous speeds? The suspects are the usual violent characters of the cosmos. Active galactic nuclei, the supermassive black holes at the hearts of galaxies, can spew jets of plasma stretching for millions of light years, potentially acting as natural particle accelerators of unimaginable scale. Gamma-ray bursts, the most energetic explosions since the Big Bang, are another prime candidate. They're relativistic jets possibly capable of imparting such tremendous energy. Yet, when astronomers look toward the rough arrival directions of the highest energy cosmic rays, they often find nothing obvious, no cataclysmic event that fits the bill. This has led to more exotic theories, from the decay of super-heavy, hypothetical particles left over from the Big Bang to defects in the very fabric of spacetime itself. The mystery is compounded by a theoretical limit known as the GZK cutoff. Protons with energies this high should interact with the faint afterglow of the Big Bang, the cosmic microwave background, and lose their energy over long distances. The fact that we detect them at all means they cannot have come from too far away, likely within a few 100 million light years. Their sources must be in our cosmic backyard, and yet they remain stubbornly hidden, ghostly snipers firing impossibly powerful bullets from the dark. Just as we map the fallout from cosmic rays, we have charted the universe's own birth certificate, a faint glow that permeates all of space. This is the cosmic microwave background, the cooled remnant of the Big Bang's first fire, a baby picture of the cosmos when it was just 380,000 years old. This radiation is incredibly uniform, a near-perfect backdrop of cold with only tiny, random fluctuations, the seeds from which all galaxies would eventually grow. This uniformity is the bedrock of modern cosmology, enshrined in the cosmological principle, which states that the universe should look roughly the same in every direction, with no special place or preferred axis. But then we looked closer. Detailed maps from satellites like Oumuamua and Planck revealed something deeply unsettling. The fluctuations in this ancient light are not completely random. They appear to be aligned along a specific axis, a preferred direction in space that has been dramatically named the axis of evil. This axis is not just a minor statistical quirk. It defines a plane across the sky, and the temperature patterns on one side of this plane seem to correlate with those on the other in a way that should not happen if the universe is truly isotropic. It is as if you drew a line through the cosmos and found that the largest structures were subtly pointing in that direction, like iron filings aligning to a magnet. The implications are staggering. If this alignment is real and not an illusion, it challenges the very foundation of the cosmological principle. It suggests the universe has a large-scale structure, a spine or a preferred orientation, which our current models of the Big Bang simply do not predict. The scientific community is deeply divided on what this means. Many argue it is a fluke, a cosmic coincidence, a trick of statistics that will vanish with more precise data or a better understanding of our own galaxy's foreground interference. After all, when you look at a field of static on an old television, your brain can sometimes pick out patterns that are not really there. The universe might be playing the same trick on us. Yet, the signal has persisted through multiple missions and increasingly sophisticated analyzers. If it is not a fluke, the possibilities are profound. Could it be a fingerprint from a time before the Big Bang, an imprint from a previous cosmic cycle? Might it be evidence that our universe is just one bubble in a vast multiverse, and this alignment is a bruise from a collision with another bubble universe in the distant past? Or does it point to a more exotic form of geometry for the cosmos, a shape that is not as simple as we once thought? The debate rages on, a quiet but fierce battle over the meaning of a pattern in the oldest light we can see, a pattern that whispers we might not understand the fundamental shape of our home at all. The very geometry of our solar system holds a sudden, sharp edge that defies prediction. Far beyond the orbit of Neptune, in the cold, dark realm of the Kuiper Belt, a vast collection of icy worlds and frozen debris circles the Sun. According to every model of how our planetary system formed, this disk of leftovers should gradually thin out with smaller and more scattered objects the farther you travel from the Sun. But that is not what we see. Instead, at a distance of about 50 astronomical units just beyond the orbit of Pluto, the number of Kuiper Belt objects plummets. It is not a gentle fade into the void, but a dramatic cliff edge, as if a cosmic gardener came along and neatly trimmed the solar system. This is the Kuiper Cliff, and its existence suggests our understanding of the solar system's outer limits is fundamentally incomplete. What could have sheared off this material so cleanly? One compelling theory points to the gravitational hand of an unseen giant. The hypothetical planet 9, a world potentially 10 times the mass of Earth orbiting in a distant, elongated path, could be the architect of this sharp boundary. Its immense gravity over billions of years might have swept the outer reaches of the Kuiper Belt clean, either hurling the objects into the Sun, ejecting them into interstellar space, or shepherding them into orbits tilted high above the solar system's plane. The gravitational influence of such a planet could also explain the bizarre, clustered orbits of several other distant objects, all pointing toward the same conclusion that a massive perturber is hiding in the perpetual twilight. Yet, not all scientists are convinced a new planet is the only answer. Another possibility reaches back into the Sun's ancient past, when our star was still nestled in its birth cluster alongside thousands of other stellar siblings. A close flyby from another star in the solar system's tumultuous youth could have gravitationally ripped away the outer material of the Kuiper Belt, truncating it and leaving behind the stark cliff we observe today. This passing star might have also been responsible for tilting the Sun's axis or stealing away the Sun's theoretical sibling star, leaving our system an only child. The Kuiper Cliff stands as a silent monument to a violent event, whether it was the slow, sculpting hand of a hidden world or the quick, catastrophic theft by a stellar intruder. This invisible boundary forces us to redraw our maps, reminding us that even in our own cosmic backyard, the final chapter of our solar system's story has not yet been written. Our solar system's carefully mapped boundaries were suddenly breached in October 2017. A watchful telescope in Hawaii, part of the Pan-STARRS Sky Survey, spotted a faint point of light moving at unprecedented speed. It was not from here. This was Oumuamua, the first known interstellar visitor, a messenger from the vast ocean between stars. Its very existence confirmed that other planetary systems routinely fling material into the void, but its characteristics were anything but routine. First, its shape, based on the extreme variations in its brightness as it tumbled end over end. Astronomers deduced it was highly elongated, perhaps 10 times as long as it was wide, a cosmic cigar or a pancake tumbling chaotically through the void. No asteroid or comet in our solar system has such a dramatic form. Then there was its silence. As it rounded the sun, astronomers expected it to develop a coma, a glowing halo of gas and dust that forms when a comet's ices heat up. Oumuamua remained starkly bare, showing no visible outgassing at all. The final and most baffling clue was its acceleration. After it slingshotted past the sun, its trajectory was meticulously tracked. It was ever so slightly speeding up, as if being pushed. This non-gravitational acceleration is common for comets, caused by jets of material acting like tiny rockets. But Oumuamua displayed no such jets, no detectable coma, no dust tail. Something was pushing it without leaving a visible trace. This triggered a fierce scientific debate that continues to this day. The leading natural explanation proposes that Oumuamua was a shard of solid nitrogen, ripped from the surface of a Pluto-like world in a distant star system. As it passed close to our sun, the nitrogen ice would have sublimated, turning directly from a solid to a gas, providing the thrust for the acceleration without producing the dusty coma typical of water-ice comets. This is an elegant solution, yet it requires a very specific and potentially rare type of object. The other, far more controversial, idea was put forward by Harvard astronomer Avi Loeb. He argued that the most straightforward explanation for the object's unusual acceleration and its bizarre shape was that it was artificial, a fragment of advanced alien technology. Specifically, he suggested it could be a light sail, a vast, thin sheet designed to be pushed by the radiation pressure from starlight. A tumbling, discarded sail from an interstellar vessel would explain the shape and the lack of visible outgassing, its motion powered by the gentle, invisible pressure of sunlight itself. Picture an artist's rendering of this enigmatic visitor, a dark, reddish, pancake-like object tumbling silently through the black, its path subtly altered by forces we can barely comprehend. Whether an exotic iceberg from a foreign Pluto or a relic from a long-dead civilization, Oumuamua's brief passage remains a profound reminder that the universe is capable of producing wonders that defy our every expectation. That silent, tumbling visitor from the stars presented a physical puzzle, but some of the deepest mysteries in the cosmos are not about objects, but about the fundamental laws of reality itself. One of these problems is so profound it pits our two most successful theories of physics against each other in a battle with the very nature of existence at stake. This is the black hole information paradox. At its heart is a simple, devastating question. If you throw something into a black hole, what happens to the information it contained? Think of a book. The paper and ink have mass and energy, sure, but the true value is the information, the specific arrangement of letters that tells a story. Now imagine burning that book. It seems destroyed, but in principle, a supremely advanced physicist could collect every single ash particle and trace of smoke, reverse the chemical reactions, and reconstruct the exact original book. In our universe, according to the unbreakable rules of quantum mechanics, information can never be truly destroyed. It can be scrambled, hidden, or rendered incredibly difficult to read, but it must, in principle, be preserved. This is a cornerstone of modern physics. Now enter the black hole as described by Einstein's theory of general relativity. Its gravity is so intense that once something crosses the point of no return, the event horizon, it is lost forever to our universe. The black hole forgets everything about what fell in. All it remembers is the total mass, electric charge, and spin. It does not care if you threw in a library of encyclopedias or a truckload of confetti. The specific information about what made those objects unique is seemingly erased from reality. This is the paradox. Quantum mechanics says information must be preserved. General relativity says the black hole destroys it. Both theories cannot be correct. Stephen Hawking discovered a way to make this conflict even worse. He realized that black holes are not completely black. Due to weird quantum effects at the very edge of the event horizon, they slowly evaporate, emitting a faint glow of particles now known as Hawking radiation. This radiation is purely thermal, random noise, like the static from an old radio. It carries no information about what fell in. So, if a black hole eventually evaporates completely, disappearing in a final puff of Hawking radiation, where did all the information about the countless stars, planets, and books that fell in over billions of years go? It appears to be permanently deleted from the universe, violating a fundamental law of physics. The search for a solution has forced physicists to propose radical ideas. One possibility is that Hawking radiation is not completely random after all. Perhaps the information is not lost inside the black hole, but is somehow imprinted onto this radiation in an incredibly subtle, scrambled code. As the black hole evaporates, it slowly leaks this encoded information back into the universe. The process would be so complex that decoding it would be practically impossible, but the information would technically be preserved. An even more mind-bending solution is the holographic principle. This theory suggests that all the information about what is inside a black hole is not stored in its vast three-dimensional volume, but is instead encoded on its two-dimensional surface, the event horizon. Imagine the information about your entire body, every cell and memory, being perfectly stored as a flat image on your skin. The three-dimensional reality we perceive inside the black hole is just a projection of this two-dimensional data. When the black hole evaporates, this surface information is transferred to the Hawking radiation, preserving it. This is not just a trick for black holes. Some physicists believe our entire universe might be a hologram, a three-dimensional projection of information stored on a distant two-dimensional boundary. Resolving the information paradox is not just an academic exercise. It is the crucial battleground where a theory of quantum gravity will be born, a framework that can finally unite the world of the very small with the realm of cosmic gravity. The answer will tell us whether our universe is, at its most fundamental level, predictable and trustworthy, or if reality itself has a delete button. Our most precise measurements of the cosmos are now in direct conflict. This is the Hubble Tension, a stubborn and growing discrepancy in one of the most fundamental numbers in all of cosmology, the Hubble constant, which tells us how fast the universe is expanding today. We have two primary, highly refined methods for measuring this rate, and they are giving us two different, incompatible answers. The first method looks back to the very beginning, to the cosmic microwave background. By mapping the tiny fluctuations in this ancient afterglow with exquisite precision, the Planck satellite could extrapolate the universe's entire expansion history, predicting what the expansion rate should be right now. This is a top-down approach, starting with the baby picture and running the film forward. The other method builds the measurement from the ground up using a cosmic distance ladder. Astronomers use pulsating stars called Cepheid variables as standard candles. These stars have a known relationship between their pulsation period and their intrinsic brightness. By measuring how bright they appear from Earth, we can calculate their distance with remarkable accuracy. We then use these Cepheids to calibrate the distances to even farther galaxies that host a specific type of supernova, an even brighter standard candle. This ladder from Cepheids to supernova gives us a direct local measurement of the universe's current expansion. Both methods are incredibly sophisticated, yet they disagree by a significant margin. The early universe method, using the cosmic microwave background, suggests a slower, more sedate expansion rate. The local universe method, using stars and supernova, insists the cosmos is expanding faster. The difference is not a small error bar, it is a gap that has only widened with better data and more precise observations. Imagine two of the world's most accurate clocks, one built from the universe's first second, the other from its present state, and they are ticking at different speeds. This discrepancy is so worrying because it points to a fundamental flaw in our standard model of cosmology, the lambda CDM model. This model has been spectacularly successful at explaining everything from the formation of galaxies to the abundance of light elements. The Hubble tension is the first crack in that solid foundation, a sign that we might be missing a crucial ingredient in our recipe for the universe. One compelling idea is that of early dark energy. This proposes that a strange, repulsive form of energy, similar to dark energy but much more potent, briefly dominated the universe in its first few 100,000 years. This extra push would have subtly altered how the early universe evolved, changing the prediction from the cosmic microwave background to align with the faster expansion rate we see today. It would be a transient phantom, a ghost in the cosmic machine that vanished long ago, leaving only this tension as its signature. Another possibility is that dark energy itself is not constant but evolving, growing stronger over time. Or perhaps our understanding of gravity needs a revision, not on solar system scales, but across the vast expanse of the entire cosmos. The graphs comparing these two measurement methods are a stark visual representation of the problem. Two lines representing our best efforts to understand reality, running in parallel but refusing to meet. Resolving the Hubble tension is not about deciding which clock is right. It is about discovering why they tell different times, a quest that may lead us to a deeper, stranger truth about the forces that shape our universe. While our cosmic clocks tick in disagreement, a perfect geometric storm rages on another world. At Saturn's North Pole, a six-sided jet stream larger than Earth has churned for decades, a colossal hexagon etched into the planet's atmosphere. This is not a fleeting cloud formation, but a persistent, rotating structure, a meteorological enigma of staggering precision and scale. The Voyager probes first glimpsed it in the 1980s, a strange, angular shadow in the fuzzy images they sent back. For years, many assumed it was a temporary feature, a lucky snapshot of a rare atmospheric event. But when the Cassini spacecraft arrived at Saturn 2 decades later, its high-resolution cameras revealed the hexagon was still there, unchanged, a permanent fixture whirling around the planet's pole. It is a wall of cloud, a raging river of wind over 20,000 miles wide, with each side longer than the diameter of our entire planet. Inside this six-sided arena, the weather is eerily calm, a vast eye of quiet encircled by a geometric hurricane. So how does nature carve a perfect hexagon on such a monstrous scale? The answer seems to lie in the physics of spinning fluids. Here on Earth, we can see a hint of this principle when we stir a cup of tea. Leaves in the center spin quickly, but they also drift toward the edges, creating a circular flow. On a much grander, faster scale, something similar is happening in Saturn's atmosphere, but with a crucial twist. Laboratory experiments and complex computer simulations show that when a fluid rotates rapidly, its internal dynamics can naturally create stable, polygonal shapes at its center. A circular jet stream can become unstable and buckle, forming waves that lock into a specific pattern. On Saturn, the conditions of wind speed, temperature, and the planet's own rotation might be just right to lock those waves into a six-sided standing wave, a pattern that reinforces itself. Yet, while we can create hexagons in spinning tanks of water, no model fully replicates the Saturn hexagon's incredible longevity and razor-sharp geometry. Why 6 sides and not 5 or 7? Why has it remained so stable for over 40 years, enduring Saturn's seasonal changes without faltering? The stunning visuals from Cassini show the hexagon in breathtaking detail, its cloud walls stacked like layers of a cake, its sharp corners tracing a path that defies the chaos of a gas giant's weather. Some theories suggest the hexagon is a deep-rooted feature, a manifestation of giant convection cells rising from far within Saturn's interior. Others propose it is a self-sustaining system, where the energy of the jet stream and the planet's rotation are locked in a perfect resonant dance. The hexagon stands as a monumental work of natural art, a puzzle written in wind and cloud that challenges our understanding of fluid dynamics on a planetary scale. It is a reminder that even within our own solar system, the laws of physics can paint with a brush of breathtaking and mysterious precision. The universe imposes a strict speed limit on its most energetic particles, a cosmic barrier born from the faint echo of creation itself. This is the Greisen-Zatsepin-Kuzmin cutoff, a theoretical wall that should prevent ultra-high energy cosmic rays from traveling vast distances across the universe. The principle is straightforward. The cosmos is not a perfect vacuum. It is filled with the cosmic microwave background, the cooled remnant of the Big Bang. For a proton traveling at nearly the speed of light, this ancient light is not a gentle glow, but a wall of high-energy gamma-ray photons. When such an ultra-high-energy proton collides with one of these background photons, it is like a speeding bullet hitting a brick wall. The collision creates a shower of new particles, sapping the proton's energy in a process known as photopion production. Over millions of light years, this process should relentlessly drain the energy of any cosmic ray that dares to travel too far, ensuring that nothing from distant galaxies can reach us with an energy beyond a specific threshold, the GZK cutoff. The universe, it seems, should be a quiet place at the very highest energies, but our detectors tell a different story. We have recorded cosmic rays with energies far beyond this theoretical limit, particles arriving with a punch that defies this fundamental law. They carry more energy than a major league fastball, all compressed into a single subatomic speck. These are the ultra-high energy cosmic rays, and their very existence is a profound anomaly. A simple diagram helps visualize this cosmic roadblock. Picture a map of the local universe with our galaxy at the center. A circle with a radius of about 150 million light-years represents the GZK horizon. From within this bubble, ultra-high energy cosmic rays can theoretically reach us, their journey short enough to avoid total energy loss. From beyond this bubble, they should be attenuated, their energy drained to levels below the cutoff. Yet, we detect particles that appear to have come from beyond this horizon, cosmic cannonballs that should have run out of fuel long before reaching Earth. So what cosmic accelerators are powerful enough to launch these particles and place them so close to our galactic doorstep? The known suspects struggle to explain the phenomenon. Active galactic nuclei with their jets of plasma are powerful, but are they powerful enough? Gamma-ray bursts are energetic, but they are too brief and too rare. Some of these ultra-high energy events seem to point back toward empty voids, regions of space with no obvious cosmic engines. This forces us to consider even more exotic possibilities. Could they be the decay products of super-heavy, hypothetical particles left over from the Big Bang, relics of a hotter, denser universe finally disintegrating in our modern era? Or might they be born from defects in the fabric of spacetime itself, cosmic strings or magnetic monopoles whose interactions could release staggering amounts of energy? The mystery of these super-cosmic rays is a double puzzle, not only of their incredible source but of their very journey. They are ghostly messengers from the most violent frontiers of the cosmos, breaking a rule we thought was fundamental and challenging us to find the invisible cannons that fired them. The very elements that forge the stars hold a secret, a single, stubborn number that refuses to add up. Our most successful model of the Big Bang, the theory of primordial nucleosynthesis, describes the universe's first few minutes with breathtaking accuracy. In that initial furnace of heat and density, protons and neutrons fuse to create the universe's first atomic nuclei. a process that should have left behind a very specific cosmic recipe. The predictions for the amounts of hydrogen and its isotope deuterium, along with helium, match the observations in ancient gas clouds and old stars almost perfectly. This agreement is one of the pillars of evidence for the Big Bang itself. Yet, for one element, lithium, the math fails spectacularly. The universe should have produced about 3 times more lithium-7 than we actually see when we look at the oldest stars in our galaxy. This is the cosmological lithium problem, a quiet but profound crack in our story of creation. How do we know how much lithium is out there? Astronomers use the fingerprints of light. When we observe the light from ancient stars, we can break it apart into a spectrum, a rainbow of colors. Dark lines appear in this rainbow at specific wavelengths, each one the unique signature of a chemical element absorbing light. By measuring the depth of the lithium absorption line, we can calculate how much of this element exists in the star's outer layers. The oldest stars, the ones that formed from the pristine gas of the early universe, consistently show only about 1/3 of the predicted lithium. It is as if someone went through the cosmos and carefully removed 2 out of every 3 lithium atoms after they were made. So where did the lithium go? Could our understanding of nuclear physics in those first few minutes be wrong? Perhaps there were unknown nuclear reactions at work, pathways that destroyed lithium as quickly as it formed. Scientists have meticulously recalculated the reaction rates, searching for a hidden channel that could resolve the discrepancy, but no conventional solution has been found. Another possibility is that these ancient stars are not the pristine time capsules we believe them to be. Maybe their internal processes over billions of years have slowly dragged surface lithium down into their hotter interiors, where it was destroyed in nuclear fires, effectively hiding it from our view. Yet, models of stellar evolution struggle to explain the uniform depletion needed to account for the missing amount across so many different stars. The most radical solution points to new physics altogether. Could exotic particles from the dark matter sector have been present in the early universe, interacting with nuclei and altering the delicate balance of fusion, specifically suppressing lithium production? This tiny anomaly, this one mismatched number in the cosmic ledger, forces us to question everything from the behavior of the first stars to the existence of particles we have not yet discovered. It is a ghost from the first 3 minutes, whispering that our picture of the universe's fiery birth is not yet complete. That stubborn mismatch of lithium hints at the violent and unstable infancy of our cosmos, a time when stellar monsters were forged in the fires of collapse. Among the most terrifying remnants of that era is the magnetar, a neutron star possessed by a magnetic field of almost biblical power. If you could bring a magnetar halfway to the moon, its magnetic field would erase the data from every credit card on Earth. This is not just a strong magnet, it is a fundamental force that warps the very nature of reality around it. A magnetar's field is a quadrillion times, that is a 1 followed by 15 zeros, stronger than the field that protects our planet. This unimaginable strength arises from a perfect storm of conditions. When a massive star dies in a supernova, its core collapses into a city-sized ball of neutrons, a neutron star. If that star was spinning rapidly and had a particularly intense magnetic field to begin with, the collapse acts like a cosmic dynamo. All those magnetic field lines are squeezed together, amplified to ludicrous levels as the core shrinks from a sphere larger than the Sun down to a diameter of barely 12 miles. The energy stored in this magnetic prison is staggering, and it occasionally breaks loose in catastrophic events known as starquakes. The crust of a neutron star is not a soft surface, but a lattice of iron nuclei 1 billion times stronger than steel. The intense magnetic stress can cause this crust to crack like the tectonic plates of Earth, but on an unimaginable scale. When it does, the star literally rings like a bell, releasing more energy in a fraction of a second than our Sun will emit over 100,000 years. This energy erupts as a blinding flash of gamma rays and X-rays, a magnetar flare that can be detected from millions of light years away, briefly outshining entire galaxies. Artistic renditions struggle to capture the sheer distortion these fields cause. Visualize space-time not as a flat grid, but as a turbulent sea, twisted into knots by the magnetar's invisible grip. The magnetic field is so strong it can actually bend the star's own solid crust, and it alters the very quantum vacuum around it, affecting how light itself propagates. The open questions surrounding these cosmic powerhouses are as profound as their fury. What is the absolute upper limit for a magnetic field in our universe? Could fields exist that are so strong they spontaneously create matter from pure energy? How exactly does a star's death create such a perfect magnetic dynamo, and why do only some neutron stars become magnetars while others do not? We are left observing these distant, ticking time bombs, wondering what other physical laws they might be bending in the dark. Our own planet's distant past holds a climate mystery that challenges our understanding of our solar system. Billions of years ago, geological evidence clearly shows that Earth was a warm, wet world with flowing rivers and vast oceans. Ancient rocks, some as old as 3.8 billion years, bear the unmistakable fingerprints of water erosion. Yet, according to our most robust stellar models, the Sun was a third dimmer in its youth. A star that week should have left our world as a global snowball, a frozen wasteland incapable of supporting liquid water, let alone the first sparks of life. This contradiction is the faint young sun paradox. Why was the early Earth not a permanent ice age? The most compelling answer points to a planetary thermostat, a powerful greenhouse effect far stronger than today's. In the primordial atmosphere, concentrations of heat-trapping gases like carbon dioxide and methane may have been hundreds of times higher. Methane, in particular, is a potent greenhouse gas, and with little oxygen in the air to break it down, it could have accumulated to create a thick, insulating blanket. This kept the planet warm under the faint glow of a young sun. Another theory suggests that the early Earth itself was darker, with less reflective land surfaces and fewer clouds, allowing it to absorb more of the sun's precious heat. A graph of the sun's increasing luminosity would show a slow, steady climb from its faint beginnings to its current brilliance, a line that, for billions of years, ran directly counter to the stable, warm temperatures recorded in our planet's oldest rocks. Even with these solutions, the paradox is not fully resolved. Geological evidence for such extreme greenhouse conditions is sparse and hotly debated. The puzzle forces us to consider that our planet's climate stability is a delicate and possibly rare dance, a balance between a star's gradual brightening and a world's ability to regulate its own atmosphere. It raises a haunting question for our search for life elsewhere. If a faint young sun is the norm for most stars, how many other Earth-like worlds never escape their ice? At the heart of our own galaxy, a strange and persistent light refuses to be explained. The core of the Milky Way should be a familiar place, dominated by the supermassive black hole Sagittarius, a star, and the dense, ancient stars that orbit it. Yet, when the Fermi Gamma Ray Space Telescope mapped this region, it revealed something unexpected, a diffuse, spherical glow of high-energy gamma rays emanating from the galactic center. This is the galactic center excess, a signal that has astronomers deeply divided over its true nature. The glow itself has a very specific energy signature, a particular pattern in the gamma ray light that acts like a fingerprint. When scientists compare this fingerprint to known cosmic objects, nothing matches perfectly. It is not the chaotic radiation from the central black hole, nor is it the uniform background from cosmic rays colliding with interstellar gas. This glow is something else entirely, a smooth, spherical halo of excess energy with no clear, conventional source. So what is generating this mysterious radiation? The two leading hypotheses take us to the frontiers of physics. The first and most thrilling possibility is that we are seeing the indirect signature of dark matter. Theoretical models suggest that dark matter particles could be their own antimatter opposites. When two of these particles collide, they would annihilate each other in a flash of pure energy, producing gamma rays with the exact kind of energy profile we observe. The dense concentration of dark matter predicted to exist at the galactic center would make it the perfect place for such annihilations to occur frequently, creating the spherical excess glow that Fermi sees. It could be the first tangible evidence of the universe's most elusive substance. The other, more conventional but equally fascinating, explanation points to a hidden city of dead stars. Millisecond pulsars are the rapidly spinning corpses of sun-like stars, neutron stars that rotate hundreds of times per second, sweeping the cosmos with beams of intense radiation. These faint, old pulsars are incredibly difficult to spot individually at such a great distance, but a vast, unseen population of thousands of them clustered at the galactic center could collectively produce the exact same smooth gamma-ray glow. Imagine a map of the galactic center, not with a single brilliant source, but with a multitude of faint, twinkling dots, each one a cosmic lighthouse, their combined light blending into the uniform excess that puzzles us. The challenge is that our current telescopes cannot resolve the glow into individual points. Is it a smooth fog of annihilating dark matter or a fine-grained sand of countless pulsars? The answer lies in the statistics of the light itself. If the glow is truly smooth, dark matter gains compelling evidence. If future observations can tease apart the signal and find that it is made up of many individual point-like sources, then the mystery is solved by pulsars. For now, the galactic center excess remains a tantalizing maybe, a cosmic Rorschach test where we see either the ghosts of dark matter or the quiet hum of a stellar graveyard, both possibilities revealing a hidden layer of reality at the core of our galactic home. Even as we map the dark, unseen architecture of the cosmos, a more fundamental kind of matter has been playing an elaborate game of hide and seek. Our most precise calculations of the Big Bang tell us exactly how much ordinary atomic matter should have been created, the protons and neutrons that scientists call baryonic matter. This is the stuff that makes up every star, every planet, and every one of us. Yet for decades, when we added up all the visible matter in the universe, from glowing galaxies to the cold gas in between, we came up embarrassingly short. A full 1/3 of all the ordinary matter that should exist was simply missing. It was a cosmic accounting error of epic proportions, a ghost in the ledger of creation itself. So where did it go? The answer appears to lie in the most desolate and vast regions of space, the immense filaments of the cosmic web that connect galaxy clusters like threads in a spider's web. Theorists suspected that the missing matter wasn't hiding in some exotic form, but was simply too diffuse and too hot to see. They named it the warm-hot intergalactic medium, or WHIM. This is not a cold, empty void, but a searing ocean of thin, ionized gas, with temperatures ranging from hundreds of thousands to millions of degrees. At such extreme heat, the gas doesn't emit visible light, and it's too thin to cast a clear shadow. Detecting it is like trying to spot the heat shimmer above a distant desert road from 1,000 miles away. The key was to find an indirect method. Astronomers realized they could use the brightest light sources in the universe as cosmic flashlights. When the light from a distant quasar travels through these filaments on its way to Earth, the superheated gas in the WHIM absorbs specific, high-energy wavelengths of that light, particularly in the X-ray and ultraviolet parts of the spectrum. It leaves a faint, telltale fingerprint in the quasar's spectrum. After years of painstaking observation, these fingerprints have finally been found, confirming that the long-lost baryons are indeed there, woven into the fabric of the cosmic web. This discovery solves one mystery while creating another. How do you map an invisible, scorching ocean that spans billions of light years? supercomputer simulations provide our best guess, painting a picture of a universe laced with these glowing, tenuous filaments, a delicate tracery of matter that contains more atoms than all the galaxies combined. The challenge now is to move from confirming its existence to truly understanding its structure and role. This missing matter is the backbone of the cosmos, the reservoir from which galaxies form and into which they eventually bleed. Finding it completes our inventory of the ordinary universe, but charting its invisible currents will define the next era of cosmic cartography. The invisible architecture of the cosmic web may be in motion on a scale we can barely comprehend. Astronomers have uncovered evidence that entire clusters of galaxies, each containing thousands of individual galaxies, are slowly rotating. These are not random, chaotic movements, but a coherent spin, a vast, lazy whirl on a scale of millions of light-years. Picture a cosmic carousel, but one where the horses are galaxies and the ride is 1 billion years long. This rotation was not seen directly, but inferred through a clever astronomical trick. Scientists measured the subtle redshift and blueshift of galaxies within these colossal clusters. Galaxies on one side of the cluster's spin were found to be moving slightly away from us, while those on the opposite side were moving slightly toward us, tracing out the signature of a slow, grand rotation. This discovery sends a tremor through our models of how the universe's largest structures form. The standard story of gravitational collapse, where regions of slightly higher density simply pull matter inward, does not easily generate such organized, large-scale spin. Gravity is a force of attraction, not rotation. So where did all this angular momentum come from? The leading theory points to the primordial universe, to the faint gravitational tides that existed when the cosmos was just a seething soup of particles. As these proto-clusters collapsed under their own gravity, they could have been twisted by the torque from these ancient tidal forces, setting them spinning like a figure skater pulling in her arms. Yet, the sheer scale of the rotation we see is difficult for even these models to fully reproduce. This is where dark matter re-enters the story. The rotation we observe is not just from the visible galaxies, but from the immense halos of dark matter in which they are embedded. It is the gravitational grip of this spinning dark matter scaffold that orchestrates the motion, suggesting that dark matter itself must have been set spinning in the early universe. Visualizations from supercomputer simulations show these clusters not as static knots in the cosmic web, but as dynamic, turning vortices, their countless galactic lights tracing out a slow, majestic dance. This immense spin forces us to ask a deeper question. How does the universe impart a twist to its largest structures? And what does this tell us about the hidden currents that flow through the dark foundations of reality? Even the slow, majestic spin of galaxy clusters cannot prepare you for a structure of such perfect geometry that it seems crafted by intelligent design. Drifting 3,300 light-years away in the constellation Monoceros, the Red Rectangle Nebula is a cosmic paradox, a dying star system that has chosen to sculpt its final breath into a series of perfect, glowing rungs. This is not a chaotic cloud of gas, but a vast, symmetrical ladder stretching into space, a sight so startling it defies our expectations of how stars die. At its heart lies a binary star system, two stars locked in a tight gravitational dance. One of them is a dying red giant, shedding its outer layers in a final, magnificent act of self-destruction. Normally, this expelled gas would form a simple, spherical shell around the star, a classic planetary nebula, but the presence of the second star changes everything. Its gravity pulls the outflowing gas, funneling it into two opposing cones that stream from the poles of the dying star. We are looking directly down the barrel of one of these cones, a perspective that creates the illusion of a rectangle. The thick, dense disk of dust surrounding the central stars acts like a belt, constricting the flow of gas and forcing it to eject primarily from the top and bottom. This is the framework, but it does not explain the ladder. the most baffling feature, the one that gives the nebula its name, is the sequence of horizontal rungs connecting the sides of the rectangle. These are not solid structures, but shock waves like sonic booms frozen in space. As the gas expands outward, it does so in fits and starts. The central binary system may be pulsing, or the ejection process might be inherently unstable, creating periodic waves of denser material that travel outward. Each time a new wave is launched, it rams into the slower-moving gas ahead of it, compressing it and causing it to glow with the rich red light of hydrogen. The result is a glowing ladder of concentric squares, a staircase to nowhere written in light and dust. High-resolution images from the Hubble Space Telescope reveal this structure in breathtaking detail, transforming what was once a smudge of red light into an intricate architectural marvel. Yet for all its beauty, the red rectangle guards its final secret closely. Why are these rungs so perfectly periodic and symmetrical? What precise clockwork within the binary system dictates the timing of these outbursts to create such a uniform ladder? The nebula stands as a sublime reminder that even in death, stars can create forms of breathtaking order, challenging us to understand the delicate physics that turns a stellar finale into a geometric masterpiece. The perfect geometry of the red rectangle is a stellar farewell, but another star recently staged a dramatic and very public performance that shook the astronomical world. Betelgeuse, the red supergiant marking the shoulder of Orion, did the unthinkable. It began to fade. In late 2019, this brilliant, familiar star, one of the brightest in our night sky, started to dim. It was not a subtle shift. This was a dramatic plunge in brightness, a descent into obscurity that captivated both scientists and the public. By February 2020, it had lost nearly 2/3 of its normal luminosity, a change visible to the naked eye. The constellation of Orion suddenly looked wounded, its shoulder blade gone dim. The most immediate and thrilling speculation was that we were about to witness a historic event, a supernova. Betelgeuse is a ticking time bomb, a star at the very end of its life, and its dramatic dimming seemed like a perfect prelude to a catastrophic explosion, a final blaze of glory that would outshine the full moon and be visible in broad daylight. The world watched, holding its breath for a cosmic fireworks show that has not occurred in our galaxy since the time of Kepler, but the fireworks never came. Instead, the star slowly, steadily began to recover its light. By April 2020, it was back to its usual brilliance. So what caused the great dimming? The culprit was not an internal collapse, but a cosmic veil. Detailed observations from the Hubble Space Telescope and other observatories revealed the truth. Betelgeuse had belched out a colossal cloud of dust. The star had ejected a titanic amount of superheated material from its surface. As this material traveled away from the star, it cooled, condensing into a vast cloud of microscopic dust grains that partially obscured our view, like a sooty smokescreen on an interstellar scale. A time-lapse of this event would show the star's southern hemisphere suddenly brightening with a hotspot, a massive upwelling of plasma, followed by the slow, dark bloom of condensing dust drifting outward, casting a shadow across the star's face and dimming its light for the entire world to see. This explanation solves the immediate mystery, but it raises a deeper, more fundamental question. What triggered such a violent and localized ejection? Was it a giant convective bubble, a plume of plasma from the star's tumultuous interior, finally bursting through the surface? Or was it linked to the star's regular pulsations, a particularly powerful beat in its slow, rhythmic breathing? The event forced us to look closer, and we discovered Betelgeuse's surface is even more chaotic than we knew. A rolling, boiling cauldron of rising and falling gas cells, each one the size of our entire solar system. The great dimming was a stark reminder that we are watching a dying star in its final, unstable acts, and we still do not know what will trigger its final bow or when the curtain will truly fall. While Betelgeuse staged its dramatic dimming, it is a mere whisper compared to the cosmic shouting match of a luminous blue variable. These are the rock stars of the stellar world, hypergiants so massive and volatile they live their entire lives on the brink of self-destruction. Eta Carinae is their most famous and terrifying representative, a binary system containing a star that may be 200 times the mass of our Sun. In the 1840s, it unleashed a colossal eruption, becoming the second brightest star in the night sky for a time, an event that should have ended in a supernova. Instead, it survived. The star did not explode, it convulsed, violently ejecting two vast lobes of gas and dust that now expand outward at millions of miles per hour. We see this structure today as the Homunculus Nebula, a breathtaking hourglass of glowing matter that utterly dwarfs our entire solar system. Visualize this nebula, a twin-lobed cloud of cosmic debris with a searingly bright central star system blazing at its heart, a permanent monument to its own near-death experience. So what drives a star to such violent, erratic behavior? Luminous blue variables are caught in a desperate tug of war between two fundamental forces. Their immense gravity, born from staggering mass, tries to crush the star inward. Meanwhile, the ferocious radiation pressure from its own nuclear fusion pushes outward with unimaginable force. For most of a star's life, these forces are in balance, but for an LBV, the balance is profoundly unstable. The radiation pressure becomes so intense that it begins to overpower gravity, making the star's outer layers swell to a truly monstrous size. The star becomes so large that its own gravity can barely hold onto its surface, and it begins to shed its skin in titanic eruptions. These are not gentle winds, but catastrophic outbursts where the star ejects multiple times the mass of our entire Sun in a single event. This represents a critical and poorly understood transitional phase. An LBV is a massive star that has exhausted the hydrogen in its core and is now fusing heavier elements, struggling to find a new equilibrium. It is a pre-supernova state, a final, frantic act before the ultimate collapse. The great mystery is why some of these eruptions, like the Great Eruption of Eta Carinae, are not the final supernova itself. What internal mechanism allows the star to blow off such an enormous amount of material without triggering a complete core collapse? Is it the influence of a binary companion stirring the internal chaos? Or is it a new type of stellar instability we have not yet modeled? These stars are cosmic loose cannons, and their violent outbursts seed the surrounding space with the heavy elements necessary for planets and life, even as they tear themselves apart in the process. Some galaxies are born from chaos, but others appear as finished works of cosmic art. Hogue's object is a galaxy of almost impossible perfection, a celestial bullseye floating in the void. It consists of a perfectly round, brilliant core of old yellow stars, encircled by a pristine, detached ring of young, hot blue stars. Between them lies a gap of profound darkness, a seemingly empty chasm that cleanly separates the two stellar populations. This is not the tangled wreckage of a galactic collision, but a structure of such symmetry it feels designed. The standard story of ring galaxy formation involves a bullseye collision, where a smaller galaxy plunges through the center of a larger disk galaxy, sending a density wave rippling outward like a stone dropped in a pond. This wave triggers star formation in a perfect ring, which is exactly what we see in objects like the Cartwheel Galaxy. But Hogue's object presents a problem. There is no sign of a perpetrator, no second galaxy that could have caused such an impact. The central core is serene and undisturbed, a round ball of stars that shows no evidence of a recent traumatic encounter. So how did this perfect ring form if not from a collision? One compelling theory points to resonant waves, long-lived ripples in a galaxy's density that can organize gas and stars into stable ring structures over billions of years. Another idea is an ancient accretion event, a scenario where a smaller, gas-rich dwarf galaxy was captured and torn apart by the larger galaxy's gravity. The captured material would have been stretched into a vast ring around the host, eventually collapsing to form the brilliant blue stars we see today. The event would have been so far in the distant past that all traces of the devoured galaxy have now vanished, leaving only this perfect circular echo. A stunning Hubble image captures its sublime geometry, a golden pearl set within a sapphire band, all floating against the black velvet of space. Hogue's object defies our categories, a beautiful outlier that forces us to question whether we truly understand all the ways a galaxy can be born. The perfect symmetry of Hogue's object suggests a cosmos of elegant order, but the equations of general relativity paint a far stranger picture, one where reality can be flipped inside out. This is the theoretical realm of white holes, a hypothetical mirror image of a black hole's crushing oblivion. If a black hole is a cosmic drain from which nothing can escape, a white hole would be its opposite, a gushing fountain that violently expels matter and energy, forbidding anything from ever entering. The concept emerges directly from the same mathematics that predicted black holes, a valid solution to Einstein's field equations when time is run in reverse. Within this framework, a black hole and a white hole could be two ends of a single tunnel connected by a wormhole, a shortcut through the fabric of spacetime. Visualize a diagram of this Einstein-Rosen bridge, a black hole's event horizon forming a throat that connects to a white hole's horizon in another part of the universe, or even in another universe entirely. It is a cosmic subway linking distant stations, a structure that promises instant travel across impossible distances. Yet, for all its mathematical elegance, this ticket likely cannot be punched. The second law of thermodynamics, which dictates that disorder in the universe must always increase, stands as an impassable barrier. A white hole, spontaneously spewing out ordered matter and energy, would effectively be a machine that decreases entropy, violating this most fundamental of cosmic rules. Most physicists therefore consider white holes impossible in our classical, stable universe. They are a beautiful ghost in the machine of general relativity, a mathematical possibility that physical reality seems to forbid. Yet, the idea persists in the most speculative corners of cosmology. Some have wondered if the Big Bang itself could be viewed as a primordial white hole, the ultimate outburst that created everything. Others theorize that if a black hole could somehow transition into a white hole, it might offer a solution to the information paradox, a way for what falls in to eventually come back out. Penrose diagrams, which map the entire lifespan of such objects, show the white hole as a singularity in the past, a beginning point rather than an end. For now, white holes remain a profound thought experiment, a reminder that our best theories of reality contain doorways to wonders we may never physically witness, cosmic fountains forever locked behind the unbreakable laws of entropy. This vast cosmic web, with its spinning clusters and elegant rings, is not uniformly filled. In the constellation of Bootes, there exists a region of nothingness so immense it defies comprehension. This is the Bootes void, a spherical abyss roughly 700 million light-years across. It is not just an empty patch, but a staggering underdensity, a hole in the universe so vast that if our Milky Way were at its center, we would have had no concept of other galaxies until the 1960s. The void contains only a few dozen galaxies, where according to our models of large-scale structure, there should be thousands. This cavern challenges the very cosmological principle, the idea that on the largest scales, the universe is smooth and homogeneous. How could gravity, which pulls matter together, leave behind a vacancy of such staggering proportions? A three-dimensional map of the nearby universe would reveal this terrifying emptiness, a spherical bubble of near-nothingness set against the glowing filaments of the cosmic web. Its existence suggests that the process of structure formation is far more complex and lumpier than we ever anticipated. The few lonely galaxies found drifting within this void are like isolated islands in an endless ocean. Intriguingly, these galaxies appear different from their cousins in the crowded clusters. They are often older, quieter, and have not undergone the rapid bursts of star formation triggered by galactic collisions and interactions. They are relics left behind in the cosmic backwater, evolving in profound isolation. Their very presence provides a unique laboratory, a control group for understanding how environment shapes a galaxy's life. So how did this void form? One theory suggests it is the result of many smaller voids merging over billions of years, like soap bubbles coalescing into one giant cavity. Another, more speculative idea is that it was carved out by the influence of a super-powerful, yet unknown, repulsive force in the early universe. The Boots void stands as a monument to our ignorance, a chilling reminder that the cosmos is capable of creating absences as profound as its presences. The perfect symmetry of Hoag's object and the vast emptiness of the Boots void are painted on the grandest of cosmic canvases, but the true nature of reality may be woven from a fabric we cannot see at all. Our most fundamental theories of physics are locked in a silent war over the very stage upon which the cosmos performs. Einstein's theory of general relativity gives us gravity, a majestic force that bends the smooth, continuous fabric of spacetime to create planets, stars, and black holes. Meanwhile, quantum mechanics governs the frantic, probabilistic dance of the subatomic world, where particles pop in and out of existence and everything is built from tiny, discrete packets of energy. Both theories are spectacularly successful in their own domains, but they are utterly incompatible. The central conflict arises when we ask what happens at the unimaginably small scale, at the heart of a black hole, or at the very moment of the Big Bang, where immense gravity meets the quantum realm. Here, our understanding of physics breaks down completely. The equations of general relativity produce nonsensical infinities, screaming that a crucial piece of the puzzle is missing. The solution may require a revolution as profound as the one Einstein himself began, a theory of quantum gravity that finally unites these two pillars of physics. This quest leads to a startling possibility that spacetime itself is not the smooth, continuous stage we perceive. Instead, it may be granular, built from tiny, indivisible units, the atoms of space and time. This concept, known as loop quantum gravity, proposes that space is woven from a network of finite loops, a fabric of a billion times smaller than an atomic nucleus. Imagine the void not as an empty expanse, but as a dynamic, foaming ocean of these fundamental quanta, constantly fluctuating and evolving. On our human scale, this quantum foam is completely invisible, its texture far too fine for any instrument to detect. The fabric appears smooth, just as a sheet of paper feels continuous even though it is made of discrete fibers. But at the ultra-tiny Planck scale, this foamy nature might become apparent, with microscopic wormholes and tunnels constantly forming and dissolving in a seething quantum frenzy. How could we ever hope to prove such an abstract idea? The challenge is immense, as these effects are trillions of times smaller than anything we can currently measure. Yet, scientists are devising incredibly clever ways to look for the fingerprints of this quantized spacetime. One approach involves the universe's most ancient light, the cosmic microwave background. As this light has traveled for over 13 billion years, its journey across the cosmos could have been subtly affected by the foamy texture of spacetime. The quantum graininess might have imprinted a unique polarization pattern on this light, a faint swirl in the afterglow of creation that next-generation telescopes could potentially detect. Another frontier lies in gravitational wave astronomy. When two black holes collide, they send ripples through the fabric of spacetime. If that fabric is truly granular, these ripples might scatter or disperse in a specific way as they travel across the universe, much like light is scattered by fog. By comparing the arrival times of gravitational waves of different frequencies from the same cataclysmic event, future observatories could potentially sense this subtle scattering effect, revealing the fine grain of reality. Visualizing this quantum spacetime is a challenge in itself, requiring abstract art that portrays a bubbling, effervescent vacuum, a turbulent sea of geometric possibility underlying the calm, ordered universe we perceive. The search for quantum gravity is the ultimate detective story, a hunt for clues hidden in the oldest light and the most violent collisions. To find them would be to finally read the fine print of the cosmic contract, to understand the rules that govern reality from the smallest speck to the largest void. The final cosmic phenomenon is the ultimate one, the fate of everything we have ever known. All the stars, galaxies, and mysteries we have explored are passengers on a journey whose final destination is determined by the greatest unknown of all, dark energy. Our cosmic forecast hinges entirely on the true nature of this phantom force, and right now, we cannot be sure which of three possible endings awaits our universe. The first, and currently most likely, scenario is the heat death, often called the Big Freeze. In this future, dark energy continues its work at its current pace, relentlessly pushing galaxies apart. The expansion of space accelerates until distant galaxies fade from view, their light stretched beyond detectability. The night sky for any future civilization would grow progressively darker and emptier. Within galaxies, stars will continue to burn through their fuel, but no new stars will form as the raw materials for star birth are locked away in dead stellar remnants and diffuse, unreachable gas clouds. One by one, the stellar furnaces will flicker out. Black holes will slowly evaporate via Hawking radiation, vanishing in a final, faint puff of particles. The universe will approach a state of absolute cold and darkness, a near-perfect vacuum where the temperature uniformly approaches absolute zero. All activity, all structure, and all life would become impossible in this vast, eternal equilibrium. It is a quiet, slow, and cold end to everything. The second possibility is far more violent and sudden, the Big Rip. This occurs if dark energy is not constant, but instead grows stronger over time, its repulsive force intensifying. In this terrifying finale, the acceleration of the universe would not just separate galaxies, it would overwhelm every force that holds things together. First, galaxy clusters would be torn apart. Then, individual galaxies would be shredded. As the force grows, the gravitational bonds holding solar systems together would snap. In its final moments, the escalating repulsion would tear planets from their stars. It would then rip apart stars and planets themselves. Finally, in the last fraction of a second, the force would exceed the nuclear forces binding atoms together, and then the very fabric of space-time would be torn asunder. Matter would be dissolved into a soup of disconnected particles, ending the universe in a single, catastrophic moment. The third, and perhaps most hopeful, model offers a form of cosmic rebirth, the Big Bounce. This cyclical theory suggests that our expanding universe is just one phase in an endless cycle. Perhaps the current expansion will eventually slow, halt, and reverse, leading to a big crunch where all matter and energy collapse back into a singularity. But instead of ending there, this ultra-dense state could trigger a new Big Bang, birthing a new universe from the ashes of the old. This cycle of expansion and contraction could have been repeating for eternity, with each new universe possessing slightly different physical constants. The key to which future becomes our reality lies in deciphering the equation of state for dark energy, a value represented by the letter W. Is it exactly -1, leading to the Big Freeze? Is it less than -1, dooming us to the Big Rip? Or does our understanding of gravity need a complete overhaul, opening the door to a cyclical cosmos? A dramatic timeline visualization would show these divergent paths. A single line representing our present day splits into three. One path stretches into an infinite, cold, dark expanse. Another path ends abruptly in a violent, jagged tear. The third path curves back on itself in a magnificent, eternal loop. We are at that branching point now, armed with curiosity and powerful telescopes, trying to read the cosmic signs that will tell us which path we are on. The ultimate fate of the universe is not just an abstract philosophical question. It is a physical one, and its answer is written in the dark, silent energy that flows through the void. These 30 cosmic enigmas are not a catalogue of our ignorance, but a map of our curiosity. They trace the very edges of our understanding, where the known universe frays into a wilderness of wonder. From the ghostly tug of dark matter to the phantom push of dark energy, from the silent scream of the wow signal to the patient dimming of Tabby's star, each mystery is a question the cosmos has posed directly to us. The universe is not a puzzle to be solved, but a story to be unraveled, and these phenomena are its most compelling and cryptic chapters. They remind us that science thrives not when it has all the answers, but when it has the courage to confront the questions that seem unanswerable. The greatest discoveries lie just beyond the light of our current knowledge, waiting in the dark for the next curious mind to find them. We have journeyed to the edge of reality, but the map is far from complete. We want to know which of these cosmic riddles captured your imagination. Was it the stellar strangeness of Betelgeuse's great dimming, the haunting geometry of the red rectangle, or the existential silence of the Fermi Paradox? Tell us in the comments which mystery you find most profound, and subscribe to join us as we continue our deep dives into the secrets of the cosmos. The universe is stranger than we can suppose, and the next great discovery is always just over the